Steve Vavrus gave a keynote address at the World Environmental and Water Resource Congress this May 2024. The Environmental and Water Resource Institute is a part of the American Society of Civil Engineers. Steve's keynote was on climate science and how it informs future design conditions. You can pause this video and take a look at a little more about Steve's background. Here are a few links that you might find useful. On Wiki, on the State Climatologist's office. If you have any questions, you can contact me at the email address shown below. And I'd like to thank the Environmental and Water Resource Institute for allowing us to distribute this recording. Thanks. I hope you enjoy the keynote.
Well, thank you, Rob, for that introduction, and thanks to the committee for inviting me here today to try to make the link between climate change and practical decision-making, which is your world. To set the stage for this, I put up a figure from Milwaukee's flood damage, right, I don't know, down the street practically from where we are. This was from a round of thunderstorms in 2010 during that summer, and so this morning's thunderstorm was right on cue, right? But really, this was small potatoes compared with the incredible flooding damage that we've been seeing in recent years around the world. And here are some examples just in the past decade. One, last year, the tragic Libyan flood, causing many thousands of deaths. Famously, 2 dams collapsed, so there was a big infrastructure component. And amazingly, about 8 months' worth of normal rainfall caused that flooding damage. And then an even bigger one in terms of rainfall was the one in Hunan in China in 2021. I still can't get over the fact that 2 feet, about 1 year's worth of normal rainfall fell during this storm. And at its peak, 8 inches per hour of rain. It's almost impossible to picture, and many billions of dollars in property damage. Closer to home, a lot of us are familiar with Hurricane Harvey down in Houston, even bigger total rainfall, more than 40 inches of rain, the costliest tropical cyclone on record. And one of the characteristics of it that made it so damaging was its very slow movement. And so it just continued to stay in about the same place, producing these prodigious rainfalls. Even closer to home, also on the topic of slow-moving weather systems, just about an hour west of here in Dane County, in that red indication where compared with Milwaukee, we had a huge torrent in August of 2018. Unofficial Wisconsin record for the most rainfall, about 1 foot fell in some places in 24 hours. Many millions of dollars in damage, infrastructure losses, roads washed out, and so on. And unfortunately, there was 1 fatality. So these sorts of flood events, are, whether they're becoming more common or whether more expensive, certainly, but they've become very prominent, and I'm just at a loss sometimes to keep up with all of them that seem to be hitting around the world. Now, one thing that we can expect based on expert assessment is that flooding is likely to become more expensive in the future. It's already really expensive, right? But according to the analysis that was published recently in the National Climate Assessment, this is the projected change in average annual flood loss from all types around the country, the U.S. And you don't want to be a green county, because if you're a green county, it means that you're likely to see more flood losses in the future. But unfortunately, the map is full of green, right? And it's worse green if you're along the Gulf Coast and the Atlantic coast. There you see the darkest colors. But even if you're inland, you're certainly not immune. Most places, including much of Wisconsin right here, indicates that we'll see more flood damage or expensive flood damage in the future. One major reason, although not the only reason, for this increase in flooding and flood damage we're expecting in the future is that rainfalls have become more intense as a result of climate change. This is an updated figure from one that's been around for many years now that shows the trend over the past several decades of the heaviest 1% of rainfalls around the U.S. And what you see is that pretty much every sector is showing some increase. The eastern half of the country in particular is showing the biggest increases of all. And right here in the upper Midwest, we've had nearly a 50% increase in the intensity of these extreme rainfalls. And in the Northeast, it's even bigger still at over 50%. So really big concern, and we'll get into some of the reasons for this later. Much of the reason for the enhanced excessive rainfall is tied to a warming climate. And there's no question about that the climate's warming. We hit a record warmth last year, highest global temperature on record since we have data in the 1800s. And here you see the temperature anomalies last year from around the world, and it was hard to escape the heat, as you can see from the map. But it's not like I cherry-picked this year, right? This is part of a long-term global warming trend that began in earnest in the 1970s. And except for some year-to-year variability, it's been pretty steady ever since. And the ocean temperatures in particular last year were extremely warm, not only because of El Nino, but other factors, and that contributed to the global warmth. Now, when we look toward the future of climate change, it's not surprising that at least in terms of temperature, we know the direction of change. It's called global warming for a reason. And when we do a scenario with computer climate models, like this one from the IPCC report, it shows for a 3-degree average global warming scenario the typical fingerprint of climate change. And that is, number one, everywhere gets warmer. Number two, land warms more than the oceans because of its lower heat capacity. And number three, polar regions, especially the Arctic, warm the most because of more ice and snow loss. So that's the temperature picture, pretty straightforward. But precipitation's a different beast, right? If I tell you the climate's changing, that doesn't tell you whether you'll get wetter or drier at your location. And in fact, the climate models indicate that it does depend greatly on where you are. For this same 3-degree warming scenario, the models indicate that certain regions of the world will get a lot wetter, one of them being the equatorial Pacific, which is the spawning grounds for El Nino. Another one being the monsoon regions of Africa and Asia, in dark green there. And then the polar regions once again, especially the Arctic, getting more precipitation with greater moisture in the atmosphere. Now, taking a step back, as a climatologist, I look at these patterns of climate change, and they're very familiar to me. These have not changed qualitatively from models for years, even decades. I think when I started as a graduate student, the maps pretty much look like this for different global warming scenarios. So in that sense, we have a lot of information that just gets reiterated, and we have a better sense of what the future will look like. But that's not enough for decision makers like yourselves. We need to do better, even though there's a lot we already know. And that brings me to an analogy here. So what I think the situation we're in reminds me of the old film, The Candidate. This is like a 50-year-old film now. And Robert Redford plays a bubblegum chewing character, a political novice who somehow manages to stage an impossible upset victory for a U.S. Senate seat. And on election night, when everyone's celebrating, he is confused and concerned and befuddled because now he realizes he's actually going to have to govern and he's actually going to have to make decisions. And so this famous line at the end of the film, he's meeting with his political consultant, and he asks the famous question, "What do we do now?" And I think that a lot of practitioners like yourselves feel the same way when it comes to climate change, whether you're an engineer or a public health official, a natural resources manager or whatnot. We have a lot of good information. Climatologists can serve as consultants, but nobody can answer this question yet precisely, what do we do now? So I'm not going to pretend to give you the answer this morning, but what I can do is break this into some bite-sized pieces that we can explore in the short amount of time we have here. So I've picked 4 likely hydrologic climate change impacts that affect future design. One of them being more intense short-term rainfalls of the like that I was describing earlier. These are storm scale, not season-long effects. And they're largely fueled by additional energy in the atmosphere and ocean, heat and water vapor. And it's something that will occur throughout the world. Nobody's going to, as long as you're in a warmer climate, you're not going to escape this process. A second one that's also a near certainty is rising global sea level. Now, this is different in the sense that it depends where you are, right? It's limited in spatial extent for direct impacts, but it's an enormous threat wherever it occurs. And it's also essentially ceaseless in time. The inertia involved in sea level rise is so long that, practically speaking, it's a forever problem from a human perspective. It's going to go on for decades, probably centuries to come. There's still more heating and sea level rise in the system. Another one that's regionally dependent is greater winter runoff, and that's affecting mainly polar or cold season climates and high elevation climates. But it's important in part because there's numerous societal implications besides infrastructure involving water availability, agriculture, and so on. And I'll contrast that with the summer rainfall or runoff changes that are less certain. And then the final one is enhanced precipitation variability. And by that I mean more frequent flip-flops between extremely wet, extremely dry, and back and forth. And this one is easy to overlook if we only look at changes in the mean. And so sometimes the variability changes are more important. And it's also a vexing one for infrastructure design because it requires thinking in both directions. If we know it's going to get wetter, you might say, well, I'll build a bigger stormwater culvert. But what if it becomes wetter and it becomes drier? Now what do you do? And so this is a really challenging one. So starting with the first item on my list, the increased short-term rainfalls, I want to bring us back to some basic physics involving the water cycle, more evaporation from lakes and streams, and transpiration from plants condenses in the atmosphere. We get precipitation, runoff, and replenish the groundwater. I don't think this is a surprise to anyone. But in a warming climate, essentially that whole process gets turbocharged. So we expect more evaporation, we expect more transpiration, more moisture in the atmosphere, leading to heavier short-term rainfalls, and greater runoff, especially in certain regions and seasons. And physically, we have a good reason why this should increase intense rainfalls, and that being that we have more moisture in a warming atmosphere because a warmer atmosphere can hold more water vapor. And we know the relationship between the two. That is, for every 1 degree Celsius increase in air temperature, the atmosphere can hold 7% more water vapor, so-called Clausius-Clapeyron relationship. And this is a real issue because if you're already starting from a warm, humid air mass that has lots of water vapor, a 7% increase can be a big absolute change. And furthermore, we know that some of the really intense rainfall events, like that one that hit Hunan, go beyond a 7% increase. They apparently are able to entrain moisture from their surroundings and really amplify that percentage even more. But at least the thermodynamics we more or less understand. A wild card that I think warrants more investigation is whether rainstorms will propagate more slowly in a warming atmosphere. That was the chief characteristic of Hurricane Harvey, as well as the storm that hit Dane County in 2018. And we have good evidence from climate models that at least the summertime circulation and jet stream will weaken during the summer in mid-latitudes. Whether that translates into slower storm propagation remains to be seen. But if it does, we now have a double whammy on our hands because thermodynamically we should get more intense rainfalls and they may persist longer. At any rate, that thermodynamic relationship is so strong that we can tell that most of the world will see increases in extreme precipitation, even in some places where there's a reduction expected in the average. So what I'm showing here is for a 4-degree global warming scenario, on the left being the annual mean climate average of precipitation change. So this is similar to the map I showed earlier, green regions getting wetter on average, brown regions drier. But the map on the right is showing for the same scenario the change in extreme precipitation events. And you notice that map is much greener. There's only a few brown places in the world, meaning that most places will see an increase, according to the models, in the extreme rainfalls, including, here's a good example, if you look at Europe, clearly a decrease in the mean precipitation, all in brown on the left, but even there, a drying climate still produces increases in extreme rainfalls when they occur. The second item on my list is global sea level rise. And as I indicated before, this is basically a slam dunk in terms of the direction of change. So the combination of thermal expansion from ocean water and greater meltwater from glaciers is almost certain going to continue increasing sea levels. They're already increasing globally. Regionally, it depends on sort of geologic characteristics of land subsidence and isostatic rebound and so on. But here we see around the U.S. that the Gulf Coast and Atlantic regions in particular have been seeing rising sea levels. It's related to the expected increase in flood costs in the future. And so those regions in particular are being hit already. And as an example, we're seeing some challenging design questions regarding high tide or sunny day flooding. These are events that aren't storm dependent. They're just because the sea level is getting so high that it's inundating coastal regions like Charleston, Miami, and other areas, flooded roads at high tides, basements getting wet, and even affecting public water delivery systems. So this is going to become an increasing problem in the future. But looking toward the future, way out to 2100, these are the projections from a climate model scenario, sort of a mid to high level estimate for the global sea level change. Anything in yellow or orange or red indicates a rise. And obviously, almost all of the world's oceans are showing an increase in the future. Now, a lot of sea level experts think that the IPCC estimate shown here is very conservative because it doesn't account for some of the potential large wildcard effects from the Greenland and West Antarctic ice sheet, but everyone agrees on the direction of change. And here again, we see the Gulf Coast and East Coast of North America being particularly vulnerable, as well as, if you look in the far north, the Arctic Ocean, Alaska, Canada, and Siberia. The third item on my list is this enhanced precipitation variability, which raises its own concerns and issues from a practical standpoint, going from episodes of too wet and to too dry. And a great local example of that occurred right here in Wisconsin last year. So the first year I was a state climatologist, I was encountered with this precipitation ping pong pattern. If you look on the bottom, this is each month of 2023 from January to December, and what's plotted is the precipitation anomaly from the long-term average. So green months being wet, brown months being dry. The first 4 months of 2023, wettest on record in Wisconsin. Nobody thought about drought. And then all of a sudden, on a dime, we flipped to the fourth driest, May through August on record, had a major drought. That was followed by a really wet October that really helped, but then we flipped back to the eighth driest November, and then slightly above average for December. So when you take the year-long average, we were just about normal, right? So what was the problem? And here again is a good example of how the variability can matter more than the mean. And what models are showing is that we can probably expect more of this precipitation variability in the future. And as an example, I show from the National Climate Assessment the frequency of transitions between 1 month precipitation extremes. So this could be going from 1 month really wet to 1 month really dry, or dry to very wet. The recent trend over the last 30 years is suggestive of an increase, at least in much of the Midwest, but not everywhere. The red areas indicate where we're seeing more of these precipitation flip-flops, but where we really need to turn our attention is the future. And regardless of the greenhouse gas emissions scenario, whether it's a low end on the left or a mid-level in the middle or a high-end emissions scenario on the right, producing major climate change, you notice that the map is becoming redder and redder, meaning that the models are suggesting we'll see more of this precipitation ping pong in the future, which is a huge issue for agriculture, obviously, but I think there's also some big infrastructure questions that you all are better equipped to deal with than anyone. But this is something to keep in mind. I feel like this is a trend in the climate change science that's becoming clearer as we proceed. The final one I want to talk about on our list is the seasonal hydrologic changes, and in particular greater wintertime runoff compared with more uncertainty in changes in summer runoff. And this is very regional dependent, but it covers much of the world, especially in the northern hemisphere. So we look at December through February and these changes in expected runoff from the recent IPCC report. The regions in green are indicative of greater wintertime runoff, anywhere up to 30, 40, 50%. And that's due to a combination of more snowmelt during the winter. So whereas before you might have a buildup of snowpack in the winter and then get a big spring flush, now we're expecting more and more that we'll have these episodes during the winter when we'll get snow and then snowmelt. And then areas that used to receive almost all their precipitation in the winter as snowfall are likely to become a greater proportion of rain, and even rain on snow, which we know produces lots of runoff. So if you're in those areas, we have pretty good confidence that that's a change we can expect. But summer is much more uncertain. Here's the corresponding map for the summer from the various models. And you see a mixture of brown and green, meaning more or less runoff during that season. And you also notice, if you look carefully, that hatching pattern, that indicates low climate model agreement. So not only is there a very good consensus in the multi-model average, but they don't agree with one another anyway. And part of the reason is not just we need to improve climate models, but summertime rainfall is a more challenging animal than wintertime or cold season precipitation. It tends to be more spotty, tend to get thunderstorm complexes that could hit there or here. It's not entirely clear. Also, soil moisture processes are difficult to simulate. And to make it even more complicated, both rainfall and soil moisture feed off on one another. And so a dry soil tends to produce less rainfall, less soil moisture. And so if you're wrong on either term, you can amplify the uncertainty in the other. So this is clearly an area that needs improvement. And as a meteorologist, I'm especially interested in the rainfall changes. And to give you a concrete example close to home, I'll show you here a case for Monroe County, Wisconsin, in the western part of the state in red. This is a collection of climate models for their projection of future summer rainfall in Monroe County. And this is some work that Rob Montgomery was highly involved in. Each circle in that figure represents a climate model estimate of summertime rainfall for Monroe County. On the left is the current climate, and you see that those blue circles are pretty close together. The future, though, is showing each model's projection for the next 30 or 50 years in the future, and here you see this huge divergence. And it's not just a divergence in the magnitude, it's a divergence in the direction. About half the models project a wetter climate in western Wisconsin, all the way up to a 20% increase. About half predict a drier future, down to a 15% decrease. If you take all the models and do model democracy and take the average, you'd say, oh, there's not going to be a change. But similar to Wisconsin's precipitation average last year, it's not the mean that matters in this case, it's the disagreement or the variability in this case among climate models. So clearly more research is warranted as we try to get a better handle on how summer rainfall will change in this area and much of the country. To kind of encapsulate what I've been describing of these 4 major hydrologic changes associated with a warming climate, I made this schematic that shows the events on 2 scales, one being geographic on the x-axis from small scale to large scale, and on the y-axis it shows the temporal scale from short time scales to long time scales. And I plotted each color-coded. The redder the coloring, the better confidence we have in each type of change. And what I think is interesting and kind of ironic is that it's the 2 at the opposite ends of the spectrum that we have the most confidence in. That being the short-term intense rainfalls in the lower left, and then the large-scale, global-scale, long-term sea level rise in the upper right. We have intermediate confidence on the middle ones, greater wintertime runoff and more precipitation variability, but admittedly those depend where you are, and it's a little squishy on exactly what time scale we're talking about. But this kind of puts things in a picture that we can digest a little more easily. Okay, so getting back to the question at hand, what do we do now? There has been some progress that I want to talk about that should leave us feeling a little better about the situation. One of which is probably not news to most of you in the audience, is the development of this new NOAA Atlas 15 that's going to provide IDF statistics that are updated, and importantly, they are going to account for a changing climate. So unlike its predecessors, which assumed a stationary climate and were funded state by state, NOAA Atlas 15 is acknowledging the changing climate, differing rainfall statistics, and it will be funded nationally by the new BIL bill. It's probably going to follow a bit of a circuitous path as shown in this diagram, but the schedule is for NOAA 15, Atlas 15 to be released in 2027, and as I said, to cover the entire country. Many of you may even be involved in the development here, but it will be an exciting change when it finally occurs. But in the meantime, there are some products that I would call kind of in-house estimate changes that are worth noting. One of which is by my colleague Dan Wright, who's an attendee from University of Wisconsin-Madison, and he's developed a methodology called stochastic storm transposition, in which he takes observed extreme rainfalls, like the one that hit Dane County in 2018, and randomly moves them around in a watershed or a geographic domain to acknowledge the fact that they could have hit anywhere within that. For instance, that storm that hit western Dane County could have landed right on the Lake Mendota watershed in Madison and caused massive citywide flooding. And if you do enough of these random realizations, you can compile a set of statistics that give you a measure of projections or estimates of things like the 10-year, 24-hour rainfall event, which he's produced into a user interface called the Wisconsin Rainfall Project. You can go online, click on a county in Wisconsin, and come up with an estimate, both for the recent past, but also projections for the future in conjunction with climate model projections. And finally, no talk these days would be complete without mention of AI. And AI is so new and so cutting edge, I don't think any of us know exactly how it's going to be applied to our situation. But there's some exciting developments in the world of climate modeling and long-range weather forecasting that makes me optimistic that this could be a very useful tool. AI has already shown a lot of promise at being very, very fast and maybe even exceeding the ability to make long-term weather forecasts compared to operational forecast models that we've been relying on. And for reasons that aren't entirely clear, it can even, in some cases, exceed the traditional ability of operational weather and climate forecast models to simulate extreme events. And to me, that's surprising because there aren't that many extreme weather events to train an AI model on, and yet it somehow seems to be doing a good job with that. We're just scratching the surface. We'll tune in later about what's going to happen, but I think this is an exciting development to be aware of. To conclude, some of the takeaway points from this morning as I see them, water-related impacts from climate change are likely to increasingly stress infrastructure. Design decisions should account for both the direction of climate change and the confidence level of a particular climate change. In some cases, we know the directions pretty well, like the warming trend, sea level rise, rainfall intensity getting greater, but we may not know the direction or the magnitude of those. But in other cases, we don't even really have a great handle on the direction of change, like summertime rainfall in many regions and the magnitude of some of these climate changes locally, which is really where the rubber meets the road in terms of you all as practitioners. But as I said, there are some reasons for optimism. Recently, there's been this acceptance of a non-stationarity of climate in design decisions and improvements in climate model projections through increasing computing power, faster simulations, higher resolution simulations, and then artificial intelligence, which has the potential to merge some of these traditional climate modeling approaches with machine learning to produce more reliable and certainly quicker and more abundant estimates of the future. So with that, I'll stop, and if we have a few minutes for questions or comments, I'm happy to hear from you. Thank you.
Okay, good. Thank you, Steve, again for the presentation. That was fantastic. One of the concerns we've been thinking about also, and you mentioned it in the winter weather precipitation, but you talked about increasing rainfall, rain on snow. But I'm from Pennsylvania and on the southeast side. I've actually been really thinking about the change in where the ice line is going to be. Is the ice line where we would primarily get icing on our roads and our streets actually going to shift north? And then how is that going to, from an application standpoint, how is that going to affect salt and salt loadings into a lot of our waters? Mm-hmm. So any thoughts about what that ice line or any projections, or do you know of any modeling that's being done to look at where the predominantly ice line is going to go? And I know it's fairly narrow.
Right, that's a great point, and I share your concern, being in Wisconsin, where traditionally we've had more of our winter precipitation in snow rather than rain and freezing rain, but we would expect that freezing rain line would shift northward in most places. Freezing rain is difficult to simulate. It's right at that transition point around 32 degrees. It depends on the atmospheric temperatures aloft, but it's a topic that people have been researching, but I definitely think it requires more information on. But if I had to put money down on it, I would say places like Pennsylvania, Wisconsin, places that typically receive a lot of snow in the winter should be expecting transition more toward freezing rain and wintertime rainfall.
Thank you. Is there anybody else? Otherwise, I have another question. So, yeah, thanks, because a lot of our work has been trying to relate snow and ice and salt. Mm-hmm. Was there somebody else? No, you're good. Okay, second question. A lot of the work we're doing as ASCE, again, is starting to focus on nature-based solutions. It's a lot of the emphasis of the federal government. How uncertain are some of these models around, particularly the summer, because we're going to be looking at vegetation selection and sensitivity of vegetation between flash flood and flash drought conditions in our nature-based solutions. So where is the modeling and where is the future of our ability to model that so we can understand plant selection?
Right. So a lot of the examples I gave for uncertainty in summer rainfall is especially in mid and higher latitudes. Lower latitudes, at least in the U.S., there is more certainty of a drying of climate, and during that season, probably both reduced summer rainfall and certainly higher evapotranspiration, which would dry out soils. So there we have some more confidence. But if we have wetter winters and springs in, say, the upper part of the U.S. is expected, and then we have drier summers, it's not entirely clear what's going to happen with vegetation, right? They might get an earlier lush spring start like we had last year in our state, but then they could quickly dry out too. So it's that boundary where things have a lot of question marks. Mm-hmm.
Steve Burgess, University of Washington. Thank you for an extremely valuable, integrative, comprehensive coverage of a difficult field. The problem with the GCMs is that I think there's something like 60 in the world right now. They've all got basically the same stuff in them with a little variation. There's an extraordinarily thoughtful colleague at GFDL who's arguing that we need about 3 GCMs and include very detailed oceanic stuff. The Southern Ocean is not included well here, and that makes all the stuff we try to do disaggregating very, very difficult. But the trends you've picked up on temperature, that's pretty obvious. The bands you're showing there of the increased precipitation in different parts of the thing is reflecting the dynamics. The reason we have things at the poles is pretty clear. But the great challenge is getting the total oceanic circulation in there. And the other thing you have there that I found very helpful was showing the variations in the world. Sea level rise is nowhere uniform. It's to do with the movement of the planet as well there. So thank you. It's more in the way of a comment, but there's another one that comes in too. You're talking about the 2 poles. We have a 3rd pole, and that's one of the most important things in the entire scheme of things because it affects about 1/3 of the world's population.
Thank you for that comment. I completely agree. Ocean simulations are critical, and they're challenging from a modeling perspective because a high-resolution atmosphere, that might be, you know, a 1/4 of a degree latitude, longitude resolution, but if you want high-resolution ocean, you need to get to like 1/10 of a degree or less to really simulate the eddies. Similarly, for simulating summertime convective storms properly, we need extremely high resolution, higher than we've been able to simulate on global platforms, global models. So this is one of the reasons I have a note of optimism at the end, is computing power is getting so much better and faster to allow these high resolution oceans to be incorporated, higher resolution convective processes in the atmosphere, and then integrating the two. And this is one of the strengths of AI, because it can run models, these emulator climate models, so much faster than traditional models that we can produce many, many ensembles to get a spread of the uncertainty. So I definitely agree with you. I share your concern. The oceans are critical. And as we saw in 2023, with the extremely warm ocean waters affecting climate, the El Nino event in the tropical Pacific affecting weather around the world, the ocean is a critical player, even if you're in the middle of a continent like we are here in Wisconsin today.
Thank you for a very nice talk and very clearly communicated. I have a question over here. Oh, I'm sorry.
Sorry, I can't see where you are. Okay.
Over here. Hi, my name's Dave, and thank you again for a nice talk. A lot of engineering projects take place at specific locations. And could you offer some of your perspective on where forecasting for very small spatial scales is headed? And oftentimes we're interested in forecasts from 1, 5, 10, 20 years. Sometimes we're interested in 50 and 100 years too, but often in shorter time scales and specific locations. And could you talk about where things are headed in the climate science, balancing statistical forecasting with on-the-ground measurements in particular locations with global climate model downscaling?
Sure, I'll do my best here. One of the things that is relevant to your question is that for a while now, actually 15, 20 years, there have been developments in downscaling global climate models to small regions on the scale of kilometers. And that can be done statistically, where you take known relationships between large-scale meteorological patterns and observe small-scale weather, and also dynamical downscaling, meaning regional climate models that can be run at very fine resolution over a limited area. So both of those have proven to have their strengths and certain weaknesses, but they could be combined in a complementary way to get better handles on questions like you're asking, small-scale effects. Right here in Milwaukee, we have a good example of that when we get lake effect snow over narrow bands in Milwaukee, or a lake breeze in the summer where you get a cooling a short ways inland. That's a very small scale process that a global climate model can't handle. So promising directions in those avenues too. Where we've always hit a limit, a wall, is that the chaos in the atmosphere or climate system has inherently limited our ability to simulate accurately beyond about 2 weeks in terms of details. We can make forecasts for a certain season depending on the type of circumstances. Like last year when we had a very strong El Nino event, we had more confidence that much of the U.S., upper U.S. would be warm and the lower U.S. would be wet, for example. But if we don't have a strong signal to latch onto, those seasonal forecasts have been pretty iffy, I would say. Getting more skillful, but still not where we want to be. And this, again, is where AI has been showing some promise in its ability to extend that limit of forecasting maybe beyond 2 weeks, at least improving the skill somewhat. So I think that the inherent chaotic nature of the climate system is going to mean we'll never have accurate forecasts, more than a short ways down the road, weeks to a month. But hopefully we can get a handle on, the upcoming season. Are we looking at mostly wetter, drier, warmer, cooler than average? I think that is in the realm of possibility, to the point where we can more confidently say, okay, this isn't just a forecast, this is something I could actually use for some practical decision making.
Sorry. I do a lot of work with design storms, and where can you see the design storm system heading in the future? Do you see the region shifting? Do you see there being like a summer design storm or a winter design storm? Where does that go in the future?
Oh, that's a good question. That's getting beyond my area of expertise. I don't know exactly what NOAA Atlas 15 is planning in terms of seasonal differences in terms of these rainfall statistics, but conceivably they're going toward that end. I really don't know the answer to that. Probably the summer climate that we're used to in terms of rainfall statistics will spread into the shoulder months, but whether that's enough to go on to have distinct seasonal differences in some of the precipitation statistics, I'm not really sure. That's probably a decision that's going to be made at a much higher level.
Hi. Hey, Steve.
Yeah.
One of the nicest lecture I ever heard on the climate, change. But I do have a question. George Gore from Rutgers University. Right now. Most of it in the room here are doing solution on the land, engineer solution, nature-based solution. I'd just like to see whether your perspective on sky solution in the skies.
So I'm sorry, the solutions
in the skies.
Oh, like geoengineering?
Yes.
Oh, okay. That's be careful what I say, right? To me, geoengineering is a last resort. If we're talking about things like shooting sulfate aerosols in the atmosphere to block sunlight, to serve as a thermostat, to temper a warming climate, I feel like the cure in some cases could be worse than the disease if we don't fully understand the implications. But nature-based solutions are a different story. Those have a lot of co-benefits, green infrastructure that can help protect wetlands, for example, while at the same time providing flood prevention. Those are a much safer route to go. But when we come to solutions in the skies, some of them have been pretty out there, both spatially and ideologically. And I think we need to be extremely careful, but we also need to be aware that the legal aspect of these things and the cost, because from what I hear, it wouldn't be that expensive to be shooting sulfates into the atmosphere to provide some offsetting cooling. But who's in charge of that? How long would that go? Who has the right to do that? What if it affects rainfall in your location in a bad way? There's just a huge number of questions, legal and scientific, that would need to be addressed before I think any of us could responsibly embrace that kind of approach toward adapting to climate change.
Well, thank you, Steve.